Okay, in this video we're going to go over this exam paper from 2024, Demonstrate Understanding of Physics. It's one of the 3 exam papers that you might sit in your level 2 physics exam for NCEA. It's achievement standard 91171. So let's have a look and see if we can unpack and answer these questions. So there are 3 questions in each paper. The first question here is called momentum and circular motion. So Jono and Tony are in the kitchen. Their dog is sitting on the floor next to them when the neighbour's dog comes in and playfully chases it around the table. So here's the dog running around the table getting chased. The dog runs in a circle on the floor around the table. Add a labelled arrow to the diagram to show the force acting on the dog as it runs in a circle at constant speed. Okay, so our labelled arrow is going to start from the centre of the mass. That's that wee dot here in the dog. Before we do that, let's just say, okay, this dog has an instantaneous velocity that is at a tangent to the circle. That's what happens when something goes around in circular motion. Because it is moving in circular motion, there must be a force, we call it a centripetal force, acting towards the center of the circular path. And because the dog is running around the circular table, the center of the circular path is in the center of the table here, and that's the centripetal force. So it said draw and label. I've drawn the arrow originating from the center of mass towards the center. I've labeled it as centripetal force, so I get an achieved grade for this. So the next thing that they want us to do is calculate the radius of the dog's path. But we note on top here that they've given us some information. The first piece of information they've given us here is the mass, and it's equal to 10 kilograms. They've also given us the velocity, here it is, and it's equal to 0.85. And the last thing here, they've given us the centripetal force, and it's equal to 15 newtons. So we now have these 3 known values, quantities, mass, velocity, FC, but we also know what they want us to find out, which is the radius. This is the unknown value. So we have 4 values: radius, mass, velocity, and FC. So we need to find the equation from our resource sheet, and that's a sheet full of physics equations that contains these 4 values: R, M, V, and FC. And of course, that equation is this equation here. FC equals mv squared over R. That's the equation for calculating the centripetal force when we have circular motion. So I'm going to substitute each of the values into each of their places, which of course we've got no value for R, so we'll just leave it as R, and we get this expression here. 15 equals 10 times 0.87 squared divided by radius. Now, if I'm proficient at rearranging equations, I remember that if I want to move radius to the other side, I multiply both sides by radius, and when I want to move the 15 to the other side, I divide both sides by 15. And actually, when I do that process, in essence, what I do is I just move something from the bottom of a fraction on one side to the top of the other side of the equation, and something that's on the top of the other side of the equation to the bottom. And in essence, they just swap places. So 15 is actually the top of a fraction. It's a 15 over 1 fraction. So whatever's on the bottom of a fraction on one side can always swap with something on the top of the fraction on the other side. I rearrange this, and then I solve this. And the answer is the radius equals 0.5 meters. Now, this is an achieved answer here. If I get this correct, I get another achieve point, or if I get this next answer correct, I can get the achieve point, but I can't. They don't add to 2 achieve points. So here, the dog has a velocity like tangent to the circular motion here. So on the other side of the table, the dog hits a slippery patch on the floor, maybe some water, and slides off at a tangent. Use physics principles to explain the dog's velocity immediately after it is moving off at a tangent. Okay, so if we're going to explain here, the first thing we're going to do is describe and then say why. So describe what's the motion like. Okay, so the dog will continue to move in a straight line because there are no unbalanced forces acting on it, right? So it's like, this is one of Newton's laws. Newton's first, every action has an equal opposite. Second law, right? So this is an object in motion will continue to stay in motion unless it is acted on by unbalanced forces. So this is our explanation on why it goes in a straight line. So the essence here is because it can no longer get friction on the floor, it can't produce centripetal force. And we need to put that point in here. So friction can no longer supply the centripetal force needed to make it turn. So it goes in a straight line because it has no unbalanced forces. Now, if I got part of this right, or I got this answer over here, I get an achieved grade. If I got both of these points right, the explanation and the calculation here, I get this merit grade. Okay, let's look at part C. The dog slides along the floor towards Jono. Jono reaches down and cushions the dog as it slides to him by putting his arms out and gradually bringing them back towards him. The dog takes 2.0 seconds to come to rest, unharmed. Use physics principles to explain why Jono put his arms out to cushion the dog rather than the dog stops quickly in 0.1 seconds. Start by calculating the force experienced by the dog in the cushion collision. Okay, so we can calculate the force in the cushion collision. So we're going to use the equation that change in momentum equals force over time. But before we can do that, let's work out the momentum of the dog. Okay, because what happens here is the dog is moving along at a specific speed and it has a certain mass. So it's going to have a certain momentum. When it's stopped, it has no velocity, so it's going to have no momentum. So whatever momentum we calculate it had as it was moving is going to equal the change momentum. So let's calculate its momentum. And what we want to do in the end, remember, is work out the force, but we're going to use a couple of equations for that. So let's calculate its momentum for a start. So the momentum of the dog is equal to its mass times its velocity. And if we look over on the left-hand side, in the previous part of the question, we're given its mass and velocity. So that's quite good. We substitute those two values in, and then we get the answer. The momentum equals 8.7 kilogram meters per second. Okay, so now we've got this momentum. Remember, this is its final, so its initial momentum, its final momentum is 0. So we know its change in momentum. So we're going to find the equation, the impulse. Remember, change in momentum is impulse equation that has both the change in momentum, the force, and the time, because we want to find the unknown thing, the force. So we're going to use this equation. Change in momentum equals force times time. So we are going to place the values that we know in here. So the change in momentum, 8.7, and the time is 2 seconds. So we get this equation. Now what we want to do is make force the subject of the equation here. So because we have 2 on the right hand side, what we're essentially doing is dividing both sides by 2 to move 2 to the other side, which is essentially, because it's multiplying on the right, we put it as division on the left hand side, and we get force equals 8.7 divided by 2. And of course that equals 4.4 newtons, rounded, okay, rounded up here. So the force equals 4.4 newtons, cool. So let's go back to what they wanted us to do. This was the first step, calculate the force, done that, awesome. But let's explain why Jono put his arms out to cushion. Okay, so we're going to be looking at this expression here. So, and we're going to say that if the change of momentum stays constant, then the force is inversely proportional to time. What do I mean by that? Well, if I rearrange this equation and I have force equals change in momentum over time, if change in the momentum stays the same, and I'm just putting it as a 1 here, it doesn't matter, then what we have is we have force on the top of the equation on the left hand side and time on the bottom of the equation on the right hand side. If I increase the time, if I make time get bigger, then force gets smaller. If I decrease time, then force gets larger. If we have something on the bottom of one side of an equation and the other thing is on the top of the other side, we say they're inversely proportional, so that when one goes up, the other goes down, or if it goes down, it goes up. So because we've said this is inversely proportional, if the time is reduced by removing the cushioning, if we make time smaller, then the force will increase. And because we increase the force, we're more likely to injure the dog. And that's our explanation. So here we get an achieved mark for calculating the force, or the momentum or the force. We get a merit mark for calculating the force, and we get an excellence for having the explanation as well. So momentum achieved, the force merit, explaining why this reduces the injury to the dog, we get the excellence. Okay, next question, next part of the question. Jono releases his 10 kilogram dog and it runs directly towards the neighbor's dog at 1.1 meters per second. So here is a diagram of his dog running towards the neighbor's. Notice his dog is moving to the left, and in this type of calculation we're going to carry out, if a velocity is moving to the left, I'm going to make it negative, and if it moves to the right, it's going to be positive. The neighbor's dog has a mass of 12 kilograms, runs directly towards Jono's dog. They collide, stick together, and slide across the floor to the right at 0.3 meters per second. Calculate the speed that the neighbor's dog was moving before the collision. Okay, so this is a collision, and it's we're going to assume here that the momentum before the collision equals the momentum after the collision. Okay, so that's always our assumption. We need to state that somewhere. So this is a momentum question. We can do a couple of things here. We have two things we can calculate the momentum of. We can calculate the momentum of Jono's dog before the collision because we know both the mass and the velocity, or we can calculate the momentum of both dogs or the whole system after the collision because we know the velocity and the mass of everything. Let's start with Jono's dog. So the neighbor's dog we know is a mass of 12. We know Jono's dog has a mass of 10 and has a velocity of negative 1.1. Remember, I said as a reference frame, we're going to make going towards the left negative and going towards the right positive. And that's going to help us out to make sure that we have our calculations correct. So the mass after of both of the dogs, of course, is 12 plus 10 is 22 kilograms, and the velocity is 0.30. That's positive because it's going to the right. Okay, so we want to calculate the speeds of the neighbor's dog. In order to know the speed of the neighbor's dog, I need to know the total momentum, and I can calculate that from the right here. I need to subtract the momentum of Jono's dog, and then I would find out the momentum of the neighbor's dog, and then if I know the momentum, I can use the mass to find the velocity. So there's a few different steps in this solving this equation. So the unknown is V2. This is what we want to find out. But before we can find it out, let's just find the momentum of Jono's dog, because we can. I've just called Jono's dog as dog number 1, okay, because most important dog, it's his dog. I'm going to put its mass in and its velocity, minus 1.1, and we get a momentum of negative 11 kilograms meters per second. Remember, the negative means it's moving towards the left-hand side. So Jono's dog momentum is negative 11. Okay, so let's find the total momentum of the dogs after the collision. So the final momentum equals the mass, the final mass, times the final velocity. So here's the final mass, 22, and the final velocity is 0.3. So the total momentum after the collision is 6.6 kilogram meters per second. Okay, so we have Jono's dog moving, has a momentum of negative 11, and the total momentum at the end is 6.6. And what we do know is that the total momentum before equals the total momentum afterwards. So we can now say that the momentum at the start was 6.6, because for a system that collides, the total momentum stays the same throughout. So we know that the total momentum at the start is 6.6. So, and the total momentum before the collision is equal to the momentum of Jono's dog plus the neighbor's dog. So we have Jono's dog plus the neighbor's dog. We have minus 11 plus, and this is the momentum for the neighbor's dog, its mass of 12 times its velocity. So this is actually all the terms substituted into this equation, and now we can solve. And we get, okay, so what we did here is we added 11 to both sides to get rid of the 11 on the right hand side, and we got 17.6 equals 12 times velocity. And then to get rid of the 12, of course, we're going to divide both sides by 12. And here we go, and we get a final velocity of 1.467 meters per second. So we round that there to 1.5 because that is the number of significant figures is 0.2 in all cases here. That's the lowest amount of significant figures, so we're going to reduce our number to that. So the velocity of Jono's neighbor's dog is 1.5 meters per second. So in this question, we can get an achieved grade if we calculated any of these momentum questions correctly. So either Jono's dog or the total momentum of the system. We can get a merit if we calculated both of these correctly and with the correct signs, and we recognize that momentum is conserved. So if we had both of these values correct, and we said that the total momentum before equals the total momentums afterwards, they give us a merit. Now the problem that often happens is when we put the values into here and rearrange them, we can make a mistake. But if you didn't make a mistake and you get everything correct, you get the excellence. So merit up until the point where we said the momentum equals before equals total momentum afterwards, excellence if you complete the whole question. Okay, so this is all of question 1 done. How do they mark it? Well, it's quite complicated when you look at physics marks. So the first thing is they are going to give you an E8 if you got 2 excellence points, 1 merit point, and 1 achieve point. That's basically all of them. If you got 2 excellence points and only 1 achieve point, or 1 excellence points, 2 merits, and 1 achieve point, they're going to give you an E7. To get an M6, you need 3 merits, or you could get the 2 E's without getting the extra M or the A, or you could get 1 E, an M, and an A. They would all give you an M6. An M5 is 2 M's plus 1 A, or an excellence and 3 A's, or an excellence and 1 merit. So you have to really carefully look and see what grades were assigned and how they add up. For achieved 4, you need 4 achieves, or if you don't have 4 achieves, you can have 1 merit, 2 achieves, or 2 merits. For A3, you can have 3 achieves, 1 merit plus 1 achieve, or 1 excellence. N2, 2 A's, or 1 M, N1, 1 A. Kind of complicated, I know, but that's how they assign the marks in this paper. Okay, so here's question 2. It's on springs and equilibrium. So Tony decides to make a cake. Tony and Jono measure 0.11 kilograms of flour using a kitchen balance, as shown below. There are 3 springs on the balance. Each gets compressed 0.01 meters when the flour is added. The simplified diagram shows the springs in the balance. This is the diagram. Okay, so before we start, let's just highlight. We've got some data here. We've got 0.011. This is the mass. We have this 0.01 meters. Now, because this is to do with the spring here, it's going to be the extension or compression of the spring. So that's X. So X equals 0.01. The next thing they wanted us to do was to add a labeled diagram. So here is my reaction force. They gave me the center of gravity here, and here is my weight force of gravity. Okay, so notice I've drawn the weight force going directly down, and the reaction force is exactly opposite. They are opposite and equal. Okay, so these forces should be balanced because this balance here is stationary. Okay, so achieved grade if I got these forces correctly drawn and labeled. They want us to now calculate the spring constant, K. So remember at the top here, we know the mass and we know the X, the distance, the compression of the spring. So we can use, we want to find K, the spring constant. So the equation we have to use here is force equals Kx. I don't know the force. So what is the actual force that the spring is acting on the spring? It's this weight force here. I know. We remember how to work out the weight force. The weight force of any object is equal to the mass of the object times the acceleration due to gravity, g, which is in this paper. If you go to the resource sheet, it's given to you 9.8. So this equation also comes from the resource sheet. I'm going to chuck these 2 values in here, 0.11 times 9.8, and that gives me a force of 1.078 newtons. Now I'm going to keep this force as it is. I'm going to use it. I'm not going to round it. In fact, I'll just keep this in my calculator for the next expression. So I want to use a spring equation here, and that is the force equals Kx. I get this also, find this from my resource sheet. And What I know here is I know the force. The weight force is actually the force that compresses the spring here, so I'm going to substitute that in for the force. And the distance that the spring is compressed is 0.01, which is x, and I'm going to move these values in here. Now I want to make k the subject of the equation. Of course, we have k multiplied by 0.01. So I need to move this to the left-hand side, and so to do that, I need to divide both sides by 0.01, which cancels it out from the right-hand side here, and my expression will be k equals 1.078 divided by 0.01. So now k equals 107.8 newtons per meter. Okay. Okay, I guess I've calculated the spring constant here, but it said here for one spring. So look here, there's 1, 2, 3 springs. Very easy to get this part wrong. I'm now going to divide the spring constant by 3 to get what the spring constant would be, because here's how it works. If I used 1.078 newtons for 3 springs, of course, a third of that weight force would be used for each one of the springs. So I just divide the whole thing by 3 and I get k equals 35.93, or I want to round this to two significant figures. I get k equals 36 newtons per meter, and that's our answer. Now in this case here, if we got the correct spring constant, they give us the achieved, that is this k equals 107.8. But if I remembered to divide it by 3, then they give me the merit. Okay, so Jono brings the groceries to the front door. Here's a choice of climbing the stairs or using a ramp. He has found that it takes less time to go up the ramp. Interesting. Compare both routes by considering the work done, the force required, and the power. Okay, so the first thing I would say here is that the same work is done in both situations because Jono is climbing the same height, right? He's gaining the same gravitational potential energy. He's doing the same amount of work because he is covering the same height distance. The second point the next thing we can talk here is that the force is equal to the work over the distance, because work equals force times distance. I've rearranged that equation, and so the force is equal to the work times distance. And if the work is kept constant, we can see that force and distance are forces on the top of an equation, force over 1, and d is on the bottom of the equation. They are inversely proportional. Force is inversely proportional to distance, and I can write this as a statement here. If this ramp has a longer distance than the stairs, then therefore the force will be less because it is inversely proportional. So because this equation, if we keep work the same, which we stated it was, then force is inversely proportional to distance. If force is smaller, if distance is larger, force must be smaller. So we've talked about the force required if you went up the ramp. Now you need less force. However, the other thing they wanted to talk about is power. Now, power equals the work over time. Now, remember we said the work stayed constant. It's the same amount of work in all instances. But we said that if we took the ramp, we took less time. Now, we can see that time is inversely proportional to power as well. If we make time less, we make power larger. So, if we make work constant, time less, power is larger. Therefore, if Jono uses less time to go up the ramp and power is inversely proportional to time, he provides more power going up the ramp. Because he took less time going up the ramp, he has to be more powerful. Okay, so this question has, if you were able to identify that the work was the same in all instances, achieved. If you were able to explain why the force will be less when you go up the ramp, it's a merit. And if you can clearly explain why, using the equation and this relationship between power and time, that it would he would have to provide more power when going up the ramp. You get an excellence here. Okay, let's have a look at the next question. Okay, so one more part to this question. So Tony is using a spice rack. Rack hanging by wires above a workbench, as shown below. The ginger spice has a mass of 0.03 kilograms and the salt 0.50 kilograms. The uniform rack has a mass of 0.37 kilograms and it is 0.4 meters long. Okay, so the ginger spice is placed 0.15 meters and the salt is placed 0.050 meters from the left-hand wire as shown. The maximum tension force between each wire can provide is 5 newtons. Now, actually, in this diagram and in the diagram in the paper, the actual width between the wires is 0.4 meters. It shows the bench being a wee bit wider, but we don't need to worry about that because we're only interested in the distance between the wires, those are reference to those distances. Okay, so if this spice rack is at equilibrium, what things have to be true? Okay, there are two statements here, one to do with torques and one to do with forces. But before we do that, let's just let's go down to part 2. So they want us to carry out a suitable calculation, decide if the wires can hold the spice. So we're going to carry out a lever calculation here. And in this case, we want to see, they said the maximum force that can come from a wire is 5 newtons. And we want to see if the spice wires can hold the rack. So if I look at this situation, it's pretty obvious that the heavy salt is sitting next to the left-hand wire. So that is going to be the force that is going to have the largest tension force acting on it. So what I'm going to do is I'm going to actually, that's going to be tension A. Tension B is going to be on the right-hand one. Let's identify the forces. So the salt is, there's a weight force coming from the salt. There's a weight force coming from the ginger spice here, and there's a weight force coming from the actual, what do we call this, piece of wood that is part of the rack. Now, if I want to carry out this calculation and I want to find out what tension force A is, so I can actually do this equation two different ways. I can either find out what tension force A is or tension force B is. If I want to find out A, I'm going to put the pivot right here at the tension force B. Now that means that tension force B will produce no torque because it's zero distance from the pivot. Anyway, that's all set up for the second part here. Let's see what they wanted us to say here. What conditions do we need for this to be at equilibrium? Well, the two conditions are that the total clockwise torques equal the total anti-clockwise torques. Now, in the actual answers to this in the exam, it said the clockwise torques equals the anti-clockwise torques. That's not true. It's the sum of all the torques, or the total of them. Okay, and the same is it's the upward forces equal the downwards forces. The total upwards forces equal the total downwards forces. Those are the two requirements for this to be at equilibrium. I couldn't do the calculations if this is at equilibrium. Now, before I do these, to do these calculations, I'm going to have to calculate the torque of each of the four forces produced that are a certain distance away from the pivot. Of course, tension force B is not going to produce a torque. So the force of the ginger here is equal to its mass times the acceleration due to gravity, which is 0.03 times 9.8. It has a force of 0.294 newtons. I can work out its torque. I'm told it's 0.15 meters away from the left-hand side wire here, I'm showing. Therefore, because I'm going to work out the distance it is from the pivot, it's 0.4 minus 0.15, which is, it's going to be 0.25 meters away from the pivot and the turning point here. So when I calculate the torque equals the force times distance, I'm going to use this force and I'm going to use a distance of 0.25 meters. And therefore I can calculate the torque that this spice container is applying is 0.0737 newton meters. Okay, so we've done that torque. Now let's do the torque of the salt. So the salt, it shows, is 0.05 meters away from the left-hand side, which means if we subtract that from 0.4, it's going to be 0.35 meters from the pivot. Before we use that, we're going to calculate the force, the weight force acting on it. The weight force is equal to 4.9, that is 0.5, that's its mass, times 9.8, acceleration due to gravity. Of course, that is negative, but we don't need to worry about the negative or positive reference in this. So now we have the torque equals the force times distance. Remember, the distance from the right-hand side wire is 0.35 meters. So we have 4.9 times 3.5, and we have a torque of 1.72. Now notice these blue forces are going to produce torques that are in the anti-clockwise direction. That is, it will rotate in the direction that is opposite to a way that a clock rotates. So we've the one thing we need to make sure we don't forget is the actual the part of the rack that supports everything. It is given a mass, so let's find out its force. Its mass is 0.37. We're going to multiply that by the gravity acceleration due to gravity, and we get a force of 3.63 newtons. The torque is going to be the distance. It's directly in the center, so it's half this distance. It's going to be 2.2 meters. So we get 3.626, the unrounded figure, times 0.2, and we get 0.725 newton meters. So now we have three torques. There are three clockwise torques, but anti-clockwise, sorry, but we only have one clockwise torques, and we know that the total clockwise, well, we can calculate the total clockwise torques, and that equals 2.51. But we know that because the total clockwise must equal the total anti-clockwise, because this is at equilibrium, and that's a truism here, that we can say the total anti-clockwise torques equals 2.51. So this force is producing a torque of 2.51 newton meters. But because we know its torque and we know its distance from the pivot, we can work out the force, the tension force that is acting on this wire. And the tension force acting on this wire, I could just call this F, but in this case I'm just calling it TA, as in tension force, equals the torque divided by the distance. So I've taken this equation up here and rearranged to make force the subject of the equation, and in this case it's the tension force, equals the torque divided by the distance. I substitute in the two values, the anti-clockwise torque and the distance, 0.4 meters, and I get this force of 6.275 newtons. Now this force here is larger than 5 newtons. So if the force is 6.27 newtons and the actual force, the maximum tension force on this wire is 5 newtons, then the wire is going to break. And what's going to happen is an actual spice rack will fall down or break, because this force is larger than the force, the maximum force that can be applied to the wire. Okay, so in this case, we're going to get an achieved if we stated the conditions correctly, or any one of the torque calculations were calculated correctly. We get a method if we did the correct method and we did a minor error, or the conditions are stated correctly and one tension force is, well, that's pretty generous. So if you get these conditions stated correctly and you calculated a tension force correctly, they're going to give you a merit. If you get the full answer, including you wrote the conclusion, you linked it back to the question, they'll give you an excellence. And that's all of question 2. Now question 2 is going to be marked exactly the same way as question 1, in that they have this peculiar way of, I think it's peculiar compared to chemistry exams, I guess, that you have to get everything right to get the E8. If you get 2 E's and 1 A, you get an E7, or 1 E, 2 merits, and 1 A. M6 is 3 M's or 2 E's. If you got the 2 E's but not the other M, that's fine. Or 1 E, 1 M, 1 A. And then we go down the line, the similar what it was to question 1. It was exactly the same, actually. Okay, let's look at question 3. Okay, so question 3 is called motion, and it's about apples. Okay, looks like this is a projectile type motion here. So Tony is going to add apples to the cake. This is the cake he was making on his balance, I guess, and I guess he was going to add some of that ginger to the cake as well. It's going to be a ginger apple cake, who knows. The apple leaves his hand at 0.65 meters per second and stops in front of Tony. It takes 4 seconds to roll along the tabletop. Wait, so let me get this. His friend Jono rolls the apple along the tabletop. Okay. Right, and it takes 4 seconds. It's going at 0. So we have a velocity here. Velocity equals 0.56 meters per second. We have a time here, and the time is 4 seconds. Calculate the acceleration of the apple. Okay, we're going to the resource sheet, and we're finding an equation to calculate the acceleration. In this case, acceleration is unknown, so we have to find the equation that has a, vi, and t, or a, v, and t. And of course, we could use this equation here. This is nice and simple. So if we go back and read this question carefully, it said the apple leaves his hand at 0.56. That's going to be the initial velocity, and stops in front of Tony, so that's 0. So the final velocity is 0, the VI is 0.56, and we know the the T, but we don't know the A. So we substitute all the values in here. Once we've substituted them in, we are going to first, using reverse BEDMAS, we're going to take away things that are added first and put them to the other side. So to get rid of the 0.56, because it's added to the other terms, the other term here is we need to subtract it. So subtract it from both sides, and we get negative 0.56 equals A times T. And to get A to the other side, of course, we divide both sides, and we get A equals negative 0.56 over 4.0. So the acceleration is 0.14 meters per second. Does that make sense? Should it be negative? Yes, it should be, because it's slowing down. Okay, so it's the acceleration. Okay, so we're quite happy with that. That's an achieved answer there, if we got that correct. So the second point is calculate the vertical and horizontal components of the initial velocity. Here, Tony now throws the apple to Jono. The angle of the throw is 40 degrees and the initial velocity is 5 meters per second, as shown in the diagram. Calculate the vertical and horizontal components of the initial velocity. Okay, so here we need to use trigonometry, so katoa. So if you remember, the first thing that we know the 40 degrees, we're going to use that in our trigonometry, and we know the tangent of the circles, of the values we're going to work out. So what we're going to try and work out is the adjacent and the opposite sides, and they were, of course, the adjacent to the angle is going to give us the horizontal, and the opposite is going to give us the vertical. So we want to find out the velocity, both the vertical and the horizontal. They're the unknown things we want to find out. Of course, to find the vertical velocity, we're going to use the opposite, so katoa, right? So 5 equals sine times 40, and we're going to get the vertical velocity equals 3.2 meters per second. And to get the horizontal component, that's adjacent to the angle, so we're going to use so katoa. So cosine 5 times cosine 40 for the horizontal velocity, and it gives us 3.8. Okay, so we're quite happy with that. Because the angle is less than 45, we expect the horizontal one to be longer than the vertical, and it is. It's 3.8 compared to 3.2, so we're quite happy with that. If we were able to calculate one of these correctly, then we get an achieved. If we calculate both correctly and we identified them as, so actually to get the achieved, you just need to carry out a correct trigonometry calculation. You don't need to identify it as vertical or horizontal. To get the merit, you had to get both answers correct with the correct identification as vertical and horizontal. Okay, next part of the question. So explain the motion of the apple shown below. Identify the type of motion. So what type of motion is the apple going through? Of course, it's been thrown and it's going a parabolic motion, so we're going to call this projectile motion. Actually, I've gone ahead here and I've started doing part 2 for A, B, and C in the appropriate diagram. Place in the forces acting on the apple and the velocity. Okay, so let's put the forces on. So because this is going to be projectile motion, the only force that's acting on the object is the force of gravity. Sorry, is the only thing acting on is the weight of gravity produced by the acceleration due to gravity. So we get the weight force happening. It's identical at each 3 places, right? We also have a velocity. What direction is the velocity? Well, the direction is here at tangent to this actual curve. So it's going to go that way for a start, okay, at the 40 degrees. And then at the top, it's going to be completely horizontal. And then it's going to be going, I guess, 40 degrees the other way down here. So we have our 3 velocities. Now remember, we said this is projectile motion. You could have said parabolic motion. I think that answer's okay as well. So we get an achieved for getting this part right. The next bit is describe how the vertical velocity of the apple changes throughout the flight. The horizontal velocity stays constant. Okay, that's always true for projectile motion. We always need to get that point down. Always say horizontal velocity stays constant throughout the journey. But, of course, the vertical velocity upwards at point A, it's 0 at point B, and it's downwards at point C. So, and at point C, it will have an equal and opposite velocity to point A. So, we could also say, because the velocity of this is changing, because there is a downwards force of gravity accelerating the apple. Okay. Now, if we were able to write those 3 points down, we get a merit point, as well as have drawn the. Actually, I think the first achieved point was to draw one of these arrows right and get this. Okay, let me go through this correctly. Achieved. Correctly identify the motion. Okay, or 3 vertical forces correct, or 3 vector velocities correct, or constant horizontal velocity throughout, or vertical velocity has constant acceleration. Okay, so you've got 4 different ways that you could get your achieved. That was to get achieved. To get merit, you had to get correct of the points we talked about. You have to get 2 of the points correct. So all arrows correct, and point 3. Point 3, all vertical. Okay, so if you had all the arrows correct and you said that vertical velocity is constant throughout the journey, you get a merit. Or you said that the acceleration is constant, you got a merit. To get excellence, you include all of what we've written down here. Okay, so the last part of the paper and the last part of this question is the ceiling is 1.5 meters above the table surface. By calculating the maximum height reached by the apple as well as the horizontal distance covered, determine whether the apple will reach Tony. So he's throwing the apple at that velocity, which was it was 3.2 vertical velocity and 3.8 horizontal velocity. Tony is 2 meters away. The maximum height of the ceiling is 1.5 meters above the table surface. Obviously he's thrown it from the table surface. Determine whether the apple will reach Tony. Okay, so what we want to do here is calculate how high the apple will go and how far the apple will go. So the maximum height and the range. So we know here that the maximum height it could go to is 1.5 meters. And down here, we know the maximum range is 2 meters, okay? So we know the vertical velocity, remember, was 2.3, and the horizontal velocity was 3.8 from previous start of this question. So the time it takes the maximum, before we can work out the maximum height, I actually have to do the first step, and that is to work out the time, and then I can use the time to work out the maximum height. Now, to find the time to reach the maximum height, the easiest way is to use this equation here. The final velocity equals initial velocity times acceleration, so plus acceleration times time. So here we know this is because we're finding the time to the maximum height, we're using the vertical velocity, and we're only using the velocities in the vertical direction. We know at the maximum height that the vertical velocity is 0. Remember, we said that on the diagram on the previous question. And we know that the first vertical velocity is 3.2. We know the acceleration because that's acceleration due to gravity, and it's negative 9.8. So we can work out what time is. So we substitute all of these values in, 0, 3.2, and negative 9.8. Well, we take the 3.2 to the other side by subtracting both sides by 3.2. And then we remove the negative 9.8 times t by dividing both sides by 9.8. And we get t equals negative 3.2 over negative 9.8. The time it takes to get to the maximum height is 0.33 seconds. Now be careful about this time. This is the time it takes for half of the journey. The time it takes to complete the full projectile motion journey is not just to the highest point, it's back to the same height as it was originally, so that would be 0.66 seconds. But in this case, we want to know the time for the maximum height, then we can work out what the maximum height is. So because we know what the time is for the maximum height, we can now work out the distance or the height for the maximum height using this equation here. We can use VF squared equals VI squared plus AD. Remember, we know what VI squared was, and we know what VF squared was, so that's kind of easy because it's 0, so that makes this term, it just gets rid of this term. We know that 3.2, and we know what the acceleration is, so we substitute in these values. 0 equals 3.2 squared plus 2 times negative 2 plus negative 9.8 times d. Once we have resolved this equation, we get d equals 10.24 over 9.6, and we get the answer of 0.5224 meters, or 0.52 meters. We can actually solve this another way. Okay, we can use this equation here because this also has distance in it, and it's easier because we don't have to rearrange it, and we just substitute the terms in. So VI 3.2 time 0.33 half times a times time squared. We put all those values in, you calculate the answer, and you get the vertical distance as 0.52 meters. Okay, so that's fine. When he throws the apple, it's not going to hit the ceiling, so it should make the journey in that way. Now let's have a look at the range. So the range, to find the range, we can only use the horizontal velocity. We said the horizontal velocity stays constant, and remember it's 3.8. So we also said we know to complete the full journey, to go from that height to the same height, it's going to take twice the time it takes to get to the highest point, so it's going to take 0.66 seconds. So distance equals velocity times time. We get distance equals 3.8 times 0.66, and we get 2.5 meters. So the apple is going to go 2.5 meters in a projectile and a parabolic path, right? It is going to reach him the range. It's not going to be at the same height because he is before it gets to the end of its path. So it's going to be a wee bit higher on its path, but that's fine. He should just be able to put his hand up and catch it. It's not going to hit the ceiling. So what we can say here is the apple will reach Tony and not hit the ceiling. Excuse me. So we get an achieve point if we found the time. Okay. So either we found the time for the full journey or half the journey. If we calculated the range, we get a merit. And if we calculated both the height, maximum height, and the range, we get an excellence. Okay, we also have to justify it. So the justifying is just say, yes, it will reach Tony. Okay, so all of this correct with the excellence. Now, just like the other two questions, they are going to give you grades depending on how many A's, M's, and E's you count up. Now, remember, when I'm talking about this, if in one part like this, if you got the E grade, you can't count the M and the A at the same time. You only count your highest grade. So when it says that you have one E, one M, and one A, you can't count these three. This is just one E. You have to now go and get an M from somewhere else and an A from somewhere else. And once you've calculated the mark that you got for each question, whether it's from an E1 to an E8, then you add those three grades up, and that will determine what overall grade you get from the paper. If you get 0 to 7, you're not achieved. If you get 8 to 13, you achieve. 14 to 18, merit, and 19 to 24 is excellence. Well, that's the 2024 paper, mechanics paper. Hopefully me going through this has helped you with some questions that you have, or to help you to carry it out with your practice of these papers. Good luck with the rest of your study.